Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussion on discretization of partial differential equations and different aspects of numerical schemes. So, in the previous lecture, we had discussed about the finite difference methods approach and then application of the principles to discretization of Laplace equation. In this lecture, let us look at the marching problems, the parabolic and the hyperbolic partial differential equations, and we will take one model equation each for studying them. So, for the parabolic problem, we are talking about the so called Stokes first problem, which is given by this equation. So, you have a first order derivative in time and a second order derivative in space associated with the viscosity coefficient. The physical problem looks like that. You have two parallel walls at a finite difference stretched between negative to positive infinity, and you have a viscous fluid in between, which is initially at rest. And at t equal to 0 plus, the first or the upper plate, upper wall or upper plate is moved towards the right with a certain velocity, let us say u infinity. So, it is given a sudden acceleration and then it continues to move with that velocity perpetually beyond that time. So, under the given circumstances, because the viscous fluid will respond to the no slip situation, it will be dragged by that upper wall and gradually the momentum will diffuse from the upper wall through the fluid to the lower layers. So, the momentum diffusivity basically occurs due to the presence of the kinematic viscosity and presence of the velocity gradient is coming into the picture because of the transport of momentum. Now, as that goes on for a long time, it ultimately takes up a linear variation, and this problem can be actually solved as an elliptic PDE when at long times there is no more variation of the u along the y direction. So, as you can see that if del u del t at some point basically becomes 0, then the problem will reduce to this. In one dimension in space, this is essentially going to be an ordinary derivative giving you this linear distribution of velocity along the y direction. Now, in order to solve this problem, we have to expand u in time also. So, we use the Taylor series to expand it in time and we obtain an expression for del u del t, which is first order accurate in time because the index is 1 here, and we substitute it on the left hand side of the governing equation, and then the right hand side is discretized using central differencing scheme, which is second order accurate, and we rearrange the terms and the final form comes up like this. Since there is only one unknown on the left hand side, all the remaining terms are coming from the previous time step, you can solve the problem using what is called as an explicit method. So, when there is only one unknown involved, you can solve the value of u at any grid point I at the next time step based on values of neighboring grid points coming from the previous time step. Now, when we solve Laplace equation, you might remember that we had used a superscript k, which stood for the iteration number or the iteration count. Here the superscript n stands for the time step. So, in terms of indices, u x t plus delta t is given by u I n plus 1, u x t is given by u I n. That is how we are trying to work it out. Here we have expanded it by writing x, but that x might as well be considered as y here, because your spatial direction is y instead of x. This can also be interpreted as y. Here it is shown in general, but whatever relevant spatial direction is involved in the problem, that has to be appropriately used. So, the index I here stands for the y location of the grid point. You have to impose initial conditions at t equal to 0 from where you start solving the problem, like you can see over here, the fluid is at rest. So, everywhere u has to be set to 0, and then you have to impose the boundary conditions on top and bottom boundaries at t greater than equal to 0. So, that is the basic framework of the parabolic problem. So, in the previous lecture you might recall, we were talking about existence of a characteristic, and information was percolating like this in a parabolic problem. So, you can very well see from the numerical scheme itself that the values, how they are influencing the next time level. So, this what you have is u I n plus 1, what you have here is u I n, this is u I minus 1 n, this is u I plus 1 n, where this is say the y direction, or you might as well use this as plus 1 and the other one as minus 1, because that will give you an appropriate field for the positive y direction. So, let us reverse that and write it that way. So, we will consider the positive y in this way, and therefore, the grid indices go like this. So, you can see how the information is percolating to update the value over here, and that is exactly matching with how we talked about the zone of dependence influencing the solution, and the characteristic line basically shows you the front which is expanding along the time direction. So, what we mean to say is that as we move along this direction, we are moving in time. As time elapses, the distribution of u changes from the leftmost one to what you have it at the center, and then at long times what you have at the right. So, that is basically giving you the characteristic direction. So, we are able to match with what we learnt in terms of characteristics. This kind of discretization is called as forward time central space discretization. If you were to do a numerical solution with a finite number of grid points, you will see that at the beginning of the solution, the grid point values will give you u's which vary like this. So, most of the fluid will be at rest, and at long times it will give you a linear distribution. That comes purely by solving this equation as a function of time. So, this is one of the marching problems that we looked at. We also look at another problem that is belonging to the hyperbolic category. So, let us choose the linear wave equation. So, we are taking the first order form of the linear wave equation. If you were taking the second order form, it would look like this. Second order form would allow two characteristics, just like the way we discussed in the previous lectures, but the first order form will allow one characteristic. So, what does that physically imply? If you look at the movement of a small ripple that you create in a medium, if it is following linear wave equation, then the propagation of that ripple as a function of time can be traced like this, that the ripple propagates through the domain unattenuated and with a certain wave speed. If you have the wave speed defined through that medium as a, then dx dt is equal to a is going to be the equation of that characteristic. This is the idea of the linear wave equation. Now, when you try to solve it using finite difference method, it is very, very important to understand what is called as the concept of upwind differencing. So, this is a problem of wave propagation or advection, and in these kind of problems you have to be very careful about the direction from which the signal is propagating, the direction from which the disturbance is propagating into the domain. So, in this case the A is positive, therefore, the disturbances are propagating towards the positive x direction. If we were to look at the second order form of the wave equation, you would see that in the x t plane, one disturbance will propagate towards the positive direction, another will propagate towards the negative direction, one will move with a velocity of plus a, another will move at a velocity of minus a. Now, as they propagate, they have a direction associated with them, that is the wave propagation direction or advection direction, that has to be accounted in the differencing scheme for the spatial derivative, very importantly. So, the spatial derivative that you have in the first order form of the linear advection equation is del u del x. So, if you want to discretize it appropriately, you have to see spatially how the grid points are located and in which direction the wave propagation is happening. So, we mark the wave propagation direction. If you are standing at this point, you have to look upstream, that means the direction from which the wave is propagating towards you, the disturbance is propagating towards you, and pick a point suitably from that direction in order to approximate the derivative. So, this is basically the backward differencing that you learnt earlier. So, we backward difference the del u del x and we represent it this way using a first order accurate representation. You can go for higher order accurate representations also, but here we have kept things simpler, and with that we will be able to accurately represent the physics by taking the appropriate direction into account, so that it is allowing the signal to propagate appropriately through the domain when we represent it through the finite difference form. When it comes to the del u del t, we are using a first order form which is often called as the Euler first order explicit time differencing. So, that gives you the form for del u del t. This gives you the form of del u del x for approximating the first order form of the linear wave equation. There is a stability requirement which is associated with this form of discretization, which is given by this interval 0 less than equal to c less than equal to 1, where c is a very, very important number in CFD. It is called as CFL number, named after three very famous scientists, Courant, Fredericks and Loewy. What it represents is the wave speed a into the time interval delta t by the space interval or the grid spacing delta x. So, a delta t is basically the distance travelled by the wave within a delta t time span, and delta x is the grid spacing. So, you are basically talking about a ratio of the distance traversed by the wave by the grid spacing through the sea. And what it says through the stability requirement is that A delta t cannot exceed delta x. So, we had a brief exposure of how you can solve the hyperbolic partial differential equation using finite difference scheme. Let us do a little more detailing on different other aspects of numerical schemes. We will look at explicit and implicit formulation, a little bit more on accuracy and stability, and measure of error, which are called as dissipative and dispersive error. Let us first look at explicit and implicit formulation. I have been mentioning the word explicit sometimes as we discuss the numerical schemes, but I have not discussed about the implicit scheme yet. Let us look at the elliptic partial differential equation category, the Laplace equation. We can have different forms, explicit forms or implicit forms. In explicit forms, at a given grid point, that is the only unknown that you have in the discrete form of the equation, where k is the iteration level. As you can see, all the neighboring values which are used in elliptic equation solution are coming from the previous iteration level, and they are already known to you. That helps you to work out that single unknown at the grid point I j. So, this is what is called as explicit formulation, where only one unknown has to be solved from that equation. The name of this iteration scheme that we have shown over here is called as the Jacobi iteration method. On the other hand, the same problem can be solved by solving for values of f at multiple grid points at the same time simultaneously, not one grid point at a time. That comes through what is called as an implicit formulation. So, the value of the function will not be available directly from one equation, but rather value of f at multiple points will be solved simultaneously through a set of simultaneous equations. Therefore, you have a system of linear equations which are often used in a very convenient form, which is called as a tridiagonal form, because there is a very efficient algorithm for solving such a matrix based problem, which is called as Thomas algorithm. We are not going to get into much detail of that here, but that is just for your information. So, here what you notice is that the values of f at 3 adjacent points I minus 1 j, I j and I plus 1 j are being solved for the k plus 1th iteration level. And what you have on the right hand side are the knowns. And this forms basically a system of equations, though we have written it as only one equation, but once you write down the values of I j numerically in a particular grid, you will understand that this forms a system. And the knowns also contain one of the terms as k plus 1 level term, because this comes from a line of values which have already been calculated. Now, this kind of iteration scheme will be called as a line Gauss serial iteration method. So, explicit and implicit formulations look like this for Laplace equation. What happens for Stokes' first problem? This we have already seen, forward time, central space. This is a first order accurate in time and second order accurate in space scheme. And if you define this collection of terms as D, which is often called as diffusion number, then we can show that in order that this numerical scheme remains stable, that errors do not become very large and the scheme does not become unstable as you calculate, you have to maintain this value, that D is less than equal to 0.5. On the other hand, if you use an implicit formulation, we are using a scheme which is called as Lassonen method. It looks like this. As you can see that here there was only one unknown at the n plus 1th level, remember this is a time step, while here k was an iteration step. There is a fundamental difference between the marching problems and the equilibrium problems. In marching problems we have time steps, in equilibrium problems we have iteration steps. So, here there are multiple terms which contain the n plus 1th time step, and therefore, they will have to be solved simultaneously. Accuracy wise, it is first order accurate in time, second order accurate in space. Interestingly, it has no stability limit whatsoever, it is unconditionally stable. That means, you are not forced to maintain values of this kind. Alright. So, here what it means is that you have to choose the delta t, delta x etcetera appropriately, so that you are able to maintain this inequality, provided that nu is a material property, it is basically the fluid property which is not under your control. So, you have to choose your time steps and your spatial grid sizes appropriately, so that the solution remains stable. But here you do not have such a restriction, it is unconditionally stable. Let us look at linear wave equation. What you notice is these are the explicit and implicit formats. We are just showing one example each. There are many other possible forms which is left to your exploration. Here we have cited Lax-Friedrich scheme for explicit, Crank-Nicolson scheme for implicit. And what you see is that again the implicit scheme is unconditionally stable, while the Lax-Friedrich scheme has a stability criterion, that the CFL number needs to be less than equal to 1. So, we could compare some of these formulations both from explicit and implicit angle, and we also looked at their accuracy as well as stability. Some important facts about accuracy of a numerical scheme. In general, higher order accuracy schemes have higher stencil sizes or larger stencil sizes in general than lower accuracy schemes. This we have already seen by comparing first order accurate and second order accurate discretizations of first order derivative. You may recall that. Second point, higher accuracy schemes can achieve reasonably satisfactory resolution of the solution features even with a moderately coarse grid. That means, you may not have a very fine mesh, you may have a rather rough or coarse mesh, but if it is a higher order accurate scheme, even on that coarse mesh, it will give you fairly good distribution of the solution features comparable with a lower order accuracy scheme which is using a much finer mesh. So, that is the magic of the higher accuracy schemes. As far as truncation error is concerned, how would it reduce if you refine the mesh? It reduces linearly on a first order accurate scheme, quadratically for a second order accurate scheme, or cubically for the third order accurate scheme, and so on. It is basically talking about the delta x to the power of 1 or to the power of 2 or to the power of 3 etcetera. I mean delta x, delta y, delta t, it applies depending on which direction you are talking about. Now, the main message is that if the grid is refined, let us say you first had a grid which was, let us say, if I call this 1, 2, 3, then it is 1, 1, 1, sorry, let us renumber the grid points. Let us say you have 1, 1 here, then you have 2, 1, then 3, 1. So, this will be 3, 2, and then you will have 3, 3. That means, this is a 3 by 3 mesh. All the remaining points also can be numbered. Now, let us say you make it a 6 by 6 mesh. That means, you are doubling your mesh size. So, now you have 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, let us add one more level here. So, that makes it 6 1. So, similarly, on the other side if you give it 6 levels, then what happens is you have a 6 by 6 mesh. What have you done? Basically, you have made the grid twice as refined. So, when you make it twice as refined, you have increased the grid size by a factor of 2. If you do that, how would the truncation error reduce? It will reduce to half if it is a first order accurate scheme, because the delta x has now become delta x by 2. For a second order accurate scheme, the delta x, it was varying as delta x square, the truncation error earlier. So, that has become delta x by 2 square, which is what? Delta x square by 4, and that is why it is reducing by a factor of 1/4. If it is a third order accurate scheme, then delta x cube on the coarser grid has now become delta x by 2 cube on the finer grid, and that is basically delta x cube by 8, and that is why it is reducing by a factor of 1/8. So, on a higher accuracy scheme, if you refine the mesh, the errors will reduce dramatically. We are also taking a look at error from another angle, which is called as either dissipative error or dispersive error. Let us say we are looking at computation of propagation of a sharp discontinuity through a one dimensional domain. So, let us say this is looking at transport of property phi through the domain, where there is a jump in the property phi at a certain location, and this whole structure is advecting at some velocity, let us say a. So, if you want to numerically compute it, how would it look like? After a while, if the scheme has more of dissipative error, the sharp jump will be kind of damped. If it is a dispersive error, what will happen? The sharp front will be captured fairly sharply, but then there will be oscillations. So, this is what is called as dispersive error. We have oscillations, and the oscillations are just around the sharp change, or often called as wiggles in the solution. So, this is the exact solution. This is a solution where dissipative error is high, and this is another solution where dispersive error is high. B and C solutions are numerical solutions, while this is the exact solution. Now, numerical solutions which are distorted primarily by dissipation errors are first order accurate methods. That means, first order accurate methods suffer from this issue, that they damp sharp gradients. Numerical solution distorted primarily by dispersion errors are typically of second order accurate methods. So, second order accurate methods suffer from these kind of oscillations. We are typically showing some numerical solution results here for you, using some of the schemes that we learnt about. The first order upwind scheme you have already learnt about. So, here there is some initial condition which has been used in the domain. This is, say, the x direction. This is the value of the dependent variable u, and u is equal to 1 for x less than equal to 0.02, which is close to this origin, and u is equal to 0 for x is greater than 0.02. This is defined at t equal to 0, and then the wave is allowed to propagate through the domain with a certain value of a. A has been defined already. So, with that the wave is propagating. You can see the jump. So, the jump was prescribed here itself. Now, as the jump moves, it gets kind of smeared, smoothed out. Why is it? Because this scheme is a first order accurate scheme, and therefore, it suffers from dissipation error. If we looked at another scheme, which is a very famous scheme called as Lax-Wendorf scheme, it is basically second order accurate. You see, it suffers from those oscillations or wiggles. The gradient is captured more sharply than the first order accurate method, but the second order accurate method suffers from dispersion error. So, these are demonstrations of what we already learnt from practical computations. So, we learnt a number of things in this lecture. We briefly discussed about discretizing marching problems, including parabolic and hyperbolic problems. Further, we discussed various aspects of numerical schemes. They included explicit and implicit formulation, accuracy and stability of numerical schemes. Finally, towards the end, we talked about dissipative and dispersion error of numerical schemes. So, when you are choosing a numerical scheme for solving a set of governing equations, you have to be very careful about these aspects which you studied in these lectures. Thank you.